let's talk a little bit about electron configuration some more. In our last lesson, we talked about how to do normal electron configuration. Now we're going to talk a little bit about when you have ions and what do you do when you have an ion and you have to write the electron configuration. Okay. First of all, a negative ion is super duper easy. Notice none of the examples here have a negative ion in them. If you have, for example, like F minus, well, regular fluorine is 1s2, 2s2, 2p5. Okay? Well, with a minus charge means you now have one additional electron. Make sure you don't mix those up. Well, basically it just means you take, instead of 2p5, it's now just 2p6. So you just add one more electron. Okay, if it's O2 minus looks exactly the same as that one, 1s2, 2s2, 2p6, because oxygen, again, normally 2p4, but with two additional electrons, it now becomes 2p6. Okay, with positive ions, it's a little bit more difficult, though. So with a positive ion, it says when you lose electrons, the electrons must be removed from the outermost shell. That is the super duper important part. Which means that when you form positive ions, elements that have electrons in the D subshell do not lose those electrons first until the S and the P subshell are also completely lost. Okay? So in general, these aren't too bad. A lot of times what I'll do is I'll write the regular electron configuration first, and then I'll go to then I'll figure out what electrons I take away. So for example, sodium is 1s2, 2s2, 2p6, 3s1. Okay, that's normal sodium. But if it's sodium plus, it means I have to take one electron away. What electrons are in the farthest shell from the nucleus? Well, certainly the third shell is the farthest one. So for Na plus, it's just 1s2, 2s2, 2p6, and that's it. Don't include that 3s. Don't put 3s0. Just write it as 1s2, 2s2, 2p6. Okay, with iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, but if you're going to take two electrons away, which you have to with Fe2+, you must take them away from the farthest shell first. Well, here's the fourth shell right here, and this is back, you're still in the third shell here. You have to remove them from the furthest shell, the outermost shell from the nucleus first. So iron with the +2 charge is just 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Notice all of those 4s2 electrons are gone. Okay, with iron with a +3 charge though, so we lost 2 electrons, now those 2 are completely gone. Now you start taking them away from the third shell. Okay, well, which one do you take them away from? You just take them away from the very last one. So once that outermost shell, once that valence shell is gone, now you just start taking them away from that last third shell. So it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 would be the correct electron configuration. Okay, for gallium, so gallium is number 31 right here on the periodic table. So again, regular gallium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay, that's regular gallium. Now gallium with a +2 charge though means we have to take 2 electrons away. Well, again, what's our outermost shell? There's the fourth shell right there. There's the fourth shell right there. So we have to take 2 away. So this, we're going to take that one away first, and then the next one we take away has to come from here. So our correct answer is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Okay, what if it was gallium 3+? Well, then, of course, we take that one away, and then the 4s would be completely gone. What if it was gallium 4+? then again, now we would have to take 1 away from that 3D subshell, so it would end up as 3D9. Okay, tin is, or sorry, did I say tin? What is it? Yes, oh yeah, that's tin. So tin right here is number 50. So again, it's going to end in 5s2. And just to kind of move things along here, tin is going to end in 5s2, 4d10, 5p2. So without showing all the other previous stuff, basically I'm trying to show just that last line there, that last period on the periodic table. If it's 4 plus, those two go away first, and then those two go away. So it would end in 4p6, and then it would go right to the 4d10. Okay, these are really, really common on the AP test, where you have to write electron configuration of positively charged ions. Okay, so make sure that when you do that, you always, again, this upper part here, that outermost shell, that's so important that you take those away first. Okay, and then the very last thing is what are called orbital diagrams. Not very common on the AP test, but they do help you figure out the number of unpaired electrons in an atom. And I'm just going to show you them here real quickly. For example, boron. Boron is 1s2, 2s2, 2p1. And what the orbital diagram looks like is you write 1s, and then you make 1 electron spinning up, 1 electron spinning down. Basically, the electrons are spinning in opposite directions. Okay, so then you go 2s, 1, 2, and then for 2p, notice I made 3 lines there. Each of those lines represents an orbital. Okay, so a p subshell has 3 orbitals. You can see here an s subshell only has 1 orbital. And in order to, these rules up here that you can read on your own time, basically Hund's rule says you have to put 1 electron in each orbital before you can start making pairs. So boron looks like this, okay, and then you've got carbon. So carbon, because carbon's 2p2, looks like that. And then nitrogen is 2p3, so nitrogen looks like this. Now that we get to oxygen, oxygen is 2p4. Now you start making pairs. And so oxygen, as you can see, has 2 unpaired electrons, where nitrogen had 3 unpaired electrons. Oxygen has 2. Fluorine, which is 2p5, looks like this, only has 1 unpaired electron right there. And then we get all the way to neon. Neon has 6, and you can see all of those orbitals are completely filled there with neon. Okay, arsenic. Okay, let's go back here to the periodic table. We're going to only show the valence electrons. Here's arsenic right here, number 33. It says to only show the valence electrons. So we're going to go 4s2, and then 4p. There's 3 electrons in that 4p subshell, so we put 1 into each orbital, and you can see that arsenic does have 3 unpaired electrons. Okay, and then our final one is what's called the ground state electron configuration and an excited state electron configuration. Every single electron configuration we've done up until now has been a ground state electron configuration, which means that all of the electrons are in the lowest possible energy level, which means you start at 1s, then you go to 2s, and then you go to 2p. A normal electron configuration is what we call a ground state, and they use that term on the AP test, is the ground state electron configuration. So when you get a ground state electron configuration, it's just a normal electron configuration, nothing special or different about that. Okay, now what's an excited state electron configuration? It means that one or more of those last electrons has been moved up to a higher energy level. It doesn't matter where, it just means that it's been moved up to somewhere different. Okay, so for example, with sodium, regular sodium, 1s2, 2s2, 2p6, 3s1. Okay, that is what we call the ground state electron configuration of sodium. Okay, an excited state just means that this last electron here gets promoted or moved up to a higher energy level. So that's why it says possible, because there's lots of different ways you could write this. I might say 1s2, 2s2, 2p6, 3p1. Or I might say 4s1. Or I might say 6p1. It doesn't matter. But when it's in an excited state, that last electron or last electrons, those valence shells have been moved, those valence electrons have been moved up to a higher energy level. Okay? So all of those were one possible excited state electron configuration. Okay, with calcium, regular calcium, 1s2, sorry, I shouldn't say regular. The ground state electron configuration of calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's a 2, sorry. Okay, so 4s2, and an excited state could be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then we could say again 5d1. Okay, in this case I only moved one electron up. Could I have moved both of them? Sure. Instead of 4s1, 5d1, it could be 3p6, 6s2. Okay, it's just one or more of those valence electrons gets promoted to the higher energy level. Okay, and that is it for electron configuration. Go do some practice problems with them.